Alright, hi Year 11, this is Mr. Lim, very croaky Mr. Lim here, and this is our video about aqueous solutions, first video, and it's about water, because aqueous means water. Alright, so we're going to be seeing why water has some fancy properties. Alright, so let's have a look here. Water is a unique substance because it has a relatively high melting boiling point, so remember that water as a covalent molecular substance is supposed to have a low melting boiling point, which it does. It's just that for all of the other covalent molecular substances, comparatively, it has a high melting and boiling point, all right, for its size. It has a lower density in solid state than in liquid state, which is a very unusual property, and we'll go through that, and high surface tension. And all of these are related to its hydrogen bonding, all right, stronger than normal hydrogen bonding, all right? So, high melting and boiling point. So each water molecule has the potential to form 4 hydrogen bonds with the water molecules around it. Now that's because when you draw out this water molecule, if you draw out this here, right, there are 2 non-bonding pairs, that's these ones here, and 2 non-bonding pairs here exposed, and 2 very positive hydrogens here. So because that is there, it can make 1, 2, 3, 4 bonds around with neighboring water molecules. And you can see that in this diagram here. 1 with the lone pair, that's that one there. 1 here, that one's that one there. 1 here, that one's that one there. 1 here, that's that one there. Okay? Now, because it can form these 4 hydrogen bonds with the water molecules around it, that's quite strong. And it's unique to water in this way. It makes a nice, pretty tetrahedral shape. All right. So each atom is therefore involved in some sort of hydrogen bond, and thus a significant amount of energy is required to disrupt the bond. So remember, whenever you talk about melting and boiling points, talk about the energy required to disrupt the bonds. All right. So this one here, lower density in solid state rather than in liquid state. So random arrangement of liquid molecule form, or well, in liquid form, the random arrangement allows the water molecules to fit closely together. So here in the cold water, you can see here the water molecules are all kind of neatly or tightly packed against each other. They can slide in nice and close to each other. All right. However, in solid form, the lattice arrangement of water, because remember they form hydrogen bonds with 4 others, they form a nice tetrahedral lattice. That just means that they're going to be a little bit further apart from each other than if they were in cold water. All right, so this structure is more spaced out than the random arrangement, therefore it's more empty space, therefore it's lower density. Okay, it's the only substance which has a lower density in solid form compared to liquid form. All right, which is very unusual, because if you think about it, when you turn into a solid, you'd expect the particles to get closer together, but in fact, in this case, the particles are getting further apart as they turn into a solid. All right, water has a maximum density at 4 degrees Celsius. Right, so that means it's the most closely packed together at 4 degrees Celsius. That means actually as you go up here, it will go from 4 degrees, 3 degrees, 2 degrees, 1 degree, and 0 degrees as the ice. Right, so because it's more dense, it will sink a bit, so the coldest water goes down to the bottom. Well, not to the bottom, like a layer underneath the bottom. All right, and this 1, 2, 3 degrees water is going to be liquid water. Okay. The floating of ice on water allows for large bodies of water to not freeze completely. So what happens is that it might be really cold up in the air, and so the ice acts as an insulating layer to the rest of the water, right? And so therefore the rest of the water doesn't freeze, only the top layer. Okay, so at sub-zero temperatures, the layers of ice insulates the water underneath. Okay, so it provides that layer. This allows water animals or aquatic animals to survive under the frozen ice and not be frozen. So all your fancy little fishies swim here in the slightly colder water and slightly warmer water underneath the ice, right? So that's why you see, like in movies and stuff, frozen lakes. You can break through a frozen lake and there's water underneath, rather than it completely freezing over if water didn't have this particular property. Right, it's really important for aquatic life to survive in really cold places. Okay, then finally, high surface tension. So surface tension is the tendency of liquids to try and be in the smallest surface area possible, right? This means that liquid particles pull into the body of the liquid, all right? So here is a water droplet. The particles on the outside generally pull towards the inside. Okay, so this is because at the surface there are attractive forces downwards and sideways, but not upwards, unlike other places in the liquid. So here is an example of that. On the surface, you've got sideways attraction, you've got more sideways attraction, and you've got downward attraction, but you've got no upward attraction here. Okay, whereas lower down in the thing, you've got water attraction going in every single direction, right? Which means that kind of there's a net zero force on this particular water molecule. There's a net zero force. But there is a net downward force on the surface molecules. And since there's a net inward force, that's that net inward force that's pulling them in together, right? So the net downward force pulls things inward, makes the surface act like a liquid, act like a stretched skin, and water has a high surface tension because of all the hydrogen bondings in that water molecule. All right, so it's a higher than normal surface tension. That's why you get all those fancy insects that can sit and stand on the waters and stuff like that. All right, so those are some fancy properties of water, stuff you need to remember. Adios.